and welcome to Networks Tech Talks presented by Samsung. I'm Tyler Kern. Today's presentation is titled Radio Access Network Evolution vRAN, and today you'll be hearing from our subject matter expert Shamik Shah, the Director of RAN Systems Engineering and Performance at Samsung Electronics America. And he's going to walk through the benefits and challenges of vRAN, vRAN architecture, and the Samsung vRAN solution advantage. So without further ado, Shamik, let me turn the floor over to you. Take it away.
Hi, my name is Shamik Shah, and I'm Director for RAN Systems Engineering and Performance with Samsung Electronics America. Today I'll be talking about the evolution of the radio access networks. We call it virtualized RAN. I will provide some of the benefits and challenges of virtualized RAN, followed by the vRAN architecture, and then kind of highlight some of the Samsung solution advantage that we bring in for the vRAN architecture and solution. So the concept of virtualized RAN utilizes, it's a combination of the IT advantages as well as the telco quality, right? So traditionally, our traditional radio access networks were deployed using vendor-specific hardware, and it had fixed capacity, whereas there's very little flexibility or dimensioning, things like that. And at the same time, with telco quality, there are certain stability, certain KPI requirements which have to be fulfilled. So now with the evolution of 5G and the different applications that are being demanded by the users, such as low latency applications, higher demand, higher bandwidth, and the traffic pattern is very robust, or it's very I mean, there are certain times where there is a lot of demand, whereas certain times there is not much demand. So it's very random. So in order to meet such requirements for our customers, we thought that the virtualized RAN would be an ideal solution, where we take the benefits from an IT industry which has developed into a fully virtualized solution, combining it with the quality and the resiliency of a wireless network. So combining the two together to meet the demands of the 5G network or the 5G use cases, virtualized RAN provides that solution. Now, some of the advantages from the IT industry that have been pulled in is hardware agnostic solution. So the operator or the vendor, we provide off-the-shelf hardware, and our software is designed to work with that hardware. So it becomes more of a virtualized solution there, and it also brings in agile type of development, where we can use the CI/CD model to bring in some advanced features. At the same time, the virtualized solution provides dimensioning, flexibility, and scaling depending on the traffic pattern or the traffic demands. As at the same time, we can efficiently manage the resources across the different servers and then obtain the pooling gain by doing so. So now that's all on the IT advantages side. Now at the same time, we still the wireless network demands a certain set of KPIs, a certain amount of stability, and the traditional network uses very key algorithms. So all of these have been developed and are now, so key algorithms, when I say some of these are like channel estimation, error correction, real-time signal and packet processing. So all of these have now been evolved to be done through software, which will now be installed on these COT servers in order to provide the same level of service and same level of KPIs to the operators. So the virtualized RAN basically is bringing in the learnings and the lessons learned from the IT industry, as well as existing radio access networks. It's important to see some of the benefits and challenges with a virtualized RAN network. So some of the key benefits that we see are scaling. Basically, the network can be scaled based on the user demands, the traffic patterns, the cell requirements, and then you can scale in, scale out, depending on whether it's off-peak hours or peak time hours. So by adding more resources and doing a lot of configuration management in order to scale the network. The other aspect of it is pooling, where you can have pooling gains in terms of sharing the resources across different cell sites and implementing certain algorithms in order to optimize and run the network efficiently. There is also an aspect of service performance, which again, a lot of automation orchestration comes in order to optimize the virtualized network. And the most important there is flexibility and cost efficient. So the goal is that the virtualized RAN will bring in cost efficiency in terms of CapEx and OpEx savings for the operators. And it will give them a flexible architecture when they deploy these networks. And we'll talk about the architecture details in the slides later on. With every new technology, every new concept, there are always challenges which, as engineers, the industry will evolve and fix those and overcome those challenges. So primarily, some of them I've listed here are the software and hardware integration competencies. So now in a virtualized network, it's primarily software driven, as I mentioned, and that's running on COTS hardware, which is off-the-shelf hardware and not a vendor-specific hardware. So obviously, there has to be a lot of integration between the hardware and the software. So now, since everything is software controlled, the deployment for virtualized networks can be located at the cell site, or it can be in a CRAN type of deployment where it's the DUs or the BBUs are located in a central location. So now, and those are connected over to the radios using a high-speed fiber. So that increases the fiber density, and that's something that the operators are looking into to invest and improve their fiber front haul network to be able to support these kind of architectural changes. And lastly, it's a new architecture, it's a new design. So obviously there are architectural changes but at the same time, it gives a lot of flexibility in deploying and trying to optimize the network so as to meet the applications and demands of the users. A key part, what I was mentioning earlier, was CapEx and OpEx savings. So this slide here highlights what we call it resource pooling and efficient utilization of resources. So the figure on the left is a standard traditional BBU deployment, where BBU is the baseband unit. So these are vendor-specific hardware, and they all come with a fixed capacity. So whether the cell is highly utilized or underutilized, the BBU capacity remains the same. And based on the traffic in those areas, some of the BBUs may be overutilized, some may be underutilized. But it's a fixed set of hardware that has to get deployed, and there is no efficiency gain in this scenario. Whereas in case of a virtualized network, where you'll have COTS servers as shown on the right, again, in certain cell areas, if there is a peak demand for traffic or for cell, there is a higher cell dimensioning requirement, we can automatically assign resources by scaling in, scaling out features, where you can utilize one of the server's full capacity and also share or pool resources from another server in order to optimize the utilization. And in this particular example, for a particular cluster, you would deploy 5 BBUs, but with a virtualized solution, you can really solve that purpose with just 4 DUs. So that itself brings in a lot of OpEx, CapEx savings, and the hardware is not vendor locked in. So it's a off-the-shelf hardware. So there are quite a few benefits, and a lot of this scale in, scale out, we call it dynamic scaling. It's all automated through orchestration that we'll talk about in the upcoming slides. The feature of dynamic scale in, scale out is very important, especially when you are trying to manage and assign resources. So again, based on the requirements at the certain geographical areas, if there are some events and then you need more resources or more cells in order to meet the traffic demands, you would trigger scale out, so that you now allocate more resources and support more cells on those locations. So similarly, at the same time, for example, when the event is over, those resources can be released and they would be available for some other purpose. So that's a very cool feature where it's more of an on-demand dynamic scaling in, scaling out of resources. The other advantage that virtualized solution brings in is zero downtime during software upgrades. So you can have version N, for example, running on the network, and the user has to brings in new features with new software, so that can be applied, and there will be a seamless transition going from a version N to version N+1. At the same time, this sets a good framework for agile type of development, which is continuous innovation, continuous development, where you can bring in the softwares in with certain limited set of features, and you're constantly providing those feature updates in order to develop your software in an agile format. So a lot of advantages that open up with the virtualized solutions. So having looked at some of the benefits and challenges, let's now look into the vRAN architecture. This slide here shows a comparison of a traditional RAN comparing it with a virtualized radio access network. So today, the diagram on the left, today we have a traditional RAN network where it's a vendor-specific DU connected through CPRI or eCPRI over to the radios or the MMUs, and then towards the northbound, it's going towards the core over the standard backhaul interfaces. And the DUs are again with a fixed capacity and vendor-specific hardware, and they are deployed at the site. In some cases, the DUs can be deployed in a cRAN type of deployment. So that's another option. Now, comparing that with a virtualized network where the certain aspects of the radio access components are virtualized, which introduces flexibility and scalability. So for example, instead of having a vendor-specific DU, we now have off-the-shelf hardware, which we call it VDU, and then the vendor installs their own software on top of those COTS servers in order to support the DU functionality. And then there are different split options where the lower layers are separated out from the RRCP-DCP as shown in this diagram. So the VCU RRCP-DCP layers are separated out into, and then they can also be split into call processing as well as like a control plane as well as a user plane functionality. So the architecture provides flexibility. So the BBU is broken into the protocols of the BBU are broken into a VDU and a VCU, and then the VCU can further be scaled based on the applications or the traffic demands in order to flexibly configure the user plane, which can be at the central location or it can be at the co-located along with the cell site based on the different type of applications. And I have an example which shows that kind of functionality. So it's a very modular architecture, very flexible, giving the operators a lot of options. So here is an example of all the different interfaces. And again, this whole architecture is supported by 3GPP, so it's a standardized architecture. It's a very disaggregated architecture. As I was explaining, that you can split the DUs as well as the CU, and even within the CU, the CP and the UP can be disaggregated and can be flexibly configured and deployed based on the traffic needs. So some of the key interfaces or some of the key aspects of this architecture is, first is the CU-DU split. So the standard introduces a specific interface, which is the F1 interface, in order to communicate between the DU and the CU. Now, within the CU's control plane, user plane, the standard defines an E1 interface to set up that communication, which basically triggers the CU-DU split and the interaction between those two components. Now, both the CU as well as the DU are, since they are virtualized, they are designed using containers, which is virtualization technology. Initially, it started off with VMs, but now we have moved on to containers, which is a much better solution. Containers using Kubernetes is very commonly used now. The other flexibility that this architecture brings in is integrated LTE and NR support. Traditionally today, all LTE networks are deployed on vendor-specific hardware. This gives an option of configuring and deploying both NR LTE using a common VDU. And in order to support the front haul demand, since the VDUs can be centrally located, the standards, there is an ORAN forum, Open RAN forum, and a specific work group, WG4, within that forum has standardized the front haul interface so that two different vendors can use the WG4 specifications to interconnect vendor one's VDU with another vendor's RU or vice versa. So very flexible, very disaggregated, modularized architecture. So now this is another view of how a CDU or a VDU looks like. So at a high level, you have the physical hardware, which we call it the COTS server. That hardware, there is a host OS which runs on that hardware, which it's the operating system. Could be Linux or any other OS operating systems. And then there is a container engine, which basically manages all the communications between the hardware specific, whereas all with the upper layers. Now, all of this is managed by the Kubernetes, and the entire control in terms of scaling, monitoring, deploying new software, all of that, capacity planning, all of that is done by Orchestrator. So the concept is same for the DU or the CU. The same hardware can be used or deployed as a DU as well as a CU. It just runs different software, and both of these are containerized. So if we take an example of the CU, you can assign resources for the control plane as well as the user plane, and that's done through orchestration. And within those, there are certain common components, software components, and there are certain scalable components, which would again be scaled in or scaled out, depends on the traffic requirements. And so that's all being done through orchestration. So it gives a lot of flexibility in deployment. And all of the standard interfaces are used to communicate with the outside network. So just like the CU, the DU follows the similar guidelines, and it has its own specific components in terms of the layer 1, layer 2 processing, and some of the very highly efficient algorithms and packet processing principles. So this gives a little more detailed view on the specific internal configuration of a DU or a CU. Another aspect which is very useful with this disaggregated architecture is improving mobility or optimizing mobility. So today, when the users move from one cell to another cell in a traditional network, they would be passing through G node B boundaries as shown on the left. So during this stage, when the user moves from one G node B to another G node B, there is a lot of signaling, a lot of traffic forwarding that has to happen, and there is a switch of the PDCP and RRC anchor from the original G node B to the source G node B to the target G node B. So a lot of signaling and a lot of traffic forwarding has to happen in a traditional architecture today, and then that basically resembles an inter G node B handover. Whereas in case of disaggregated architecture, the VCU can basically control multiple VDUs. So your G node B is now split such that you can have multiple DUs being managed by a single VCU. So basically when the same user, let's say it's moving across the VDU boundaries. So in that case, since both the VDUs are managed by the same VCU, there is no traffic forwarding required. There is no anchor switch, because now since the VCU now has the RRC PDCP layers, there is no need for switching the anchor. So all it will do is just, instead of sending traffic to one VDU, it will now send it to the other VDU. So lot of signaling is avoided, and which basically all in short, it all results in better mobility performance and a more stable, more optimized network. So a good architectural design to improve and maintain key KPIs. Another aspect that I mentioned earlier was flexibility, especially with the CU-UP architecture. So the CU-UP is the user plane of the VCU. So what this helps is the UP can be located at the data center, or it can be configured to be used at the cell site. Now, why do we do this, right? So it really depends on the application. So let's say the operator has users who require like eMBB type of traffic, which is very bandwidth specific, where they need a higher capacity, but they don't really care about latency, right? So in that case, the UP can be co-located at the data center or at the central location along with the CP, and then it can be scaled so that it can support higher capacity. Now, at the same time, another application such as mobile edge computing or URLLC, which is very low latency type of V2X type of communication. So in those cases, since latency is of a key requirement, the UP functionality can be co-located with the cell site, so that that helps with the reducing the latency. So in such cases, bandwidth is not of key concern, but latency is more important. So signaling, latency, all of that can be handled and managed flexibly. Now, this particular framework sets up what we call network slicing. So the next slide basically I'll show you an overview of end-to-end network slicing, but because of this flexibility, slicing becomes very easy to manage in a virtualized network. So here are three different service flows based on the applications. As I was explaining earlier, eMBB slice and the URLLC slice. So depending on the type of applications, the CP and UP can be deployed in a certain fashion, where they can be deployed at the edge data center, or they can be co-located with the cell site, so, or at the regional data center. So the standard and the architecture allows this flexibility to be able to support this, and overall slicing can be managed end to end, right from the core all the way to the edge data centers and to the cell sites and the users. So the key question now comes up is, so how does all this scale in, scale out, automated or dynamic scaling happens? How does the orchestrator get that information, or what does it need to do to make such decisions, right? So this picture here basically shows at a high level of how the orchestrator gets the data, and then it has its own inbuilt algorithm or thresholds which would trigger automated responses in order to perform the certain task depending on what's been configured. So the orchestrator is constantly monitoring or getting data from the vRAN applications using the containerized platform. So in containers, basically we use the software functions are called pods. So the orchestrator is actually monitoring the status of these pods. And it also gets information like any alarms or any CPU load, or it even provides gets information from the EMS, which is the element management system, which basically controls all the different cell sites and provides information such as KPIs, alarms. So all of that is taken by the orchestrator, and it's constantly monitoring it. Now on the orchestrator, it can be automated, and you can define certain thresholds so that functions such as scaling in, scaling out can be done automatically. And so as soon as, based on the data that the orchestrator receives and the configuration that's been set up, the orchestrator makes decisions, and and sends instructions to the pods on the vRAN application using the containerized platform, and basically to increase the capacity or decrease depending on the traffic demands. So this is all fully automated. Another key advantage that this whole architecture brings in is analytics. So these days, the industry is also relying a lot on automation and analytics. So this is done very easily through a virtualized orchestrator controlled network. So these slides cover an overall concept of a virtualized RAN network, and I have covered some of the key aspects. A disaggregated architecture, the flexibility, as well as the how a CU and the DU looks like, as well as how the orchestrator manages the monitoring, as well as the scaling in, scaling out functionalities. So the next part, what I wanted to highlight was the Samsung's advantages in bringing in these solutions. So Samsung has a very wide experience being in the business for over 20 years, and we have defined very detailed algorithms for layer 1, layer 2, such as cell detection, channel estimation. So all of these algorithms have been optimized and have been implemented in order to work in a virtualized network. So it's built from a market-proven radio access network, and our experience and our learnings have been adopted to be able to work on a virtualized platform. The reason is we still have to meet the stability, the KPIs, the real-time processing. So all of those functionalities have to be developed now on vendor-agnostic hardware. So it's all becoming software-driven. So so that's one. The other part is through software upgrades, we can support both LTE and NR on a DU. So that's an additional advantage. We utilize microservice and container-based architecture. As I explained, it's all highly agile software-based architecture, which optimizes resource pooling and supports scaling dynamic, and it's fully automated. Stability and flexibility is another key aspect that we highly focused on. We have high availability protocols and functions that have been implemented in order to support these flexible deployment architecture. And overall end-to-end automation and orchestration, as the industry is moving more into automation and analytics. Our design supports fully automated VCU, VDU, RU deployments, all done through a centralized orchestrator. And we also support end-to-end network slicing. That's an innovative solution there. And we also are closely following the ORAN, Open RAN interfaces. So we are compliant with that as well. So all in all, we expect that the virtualized solutions brings in flexibility for all the future cutting-edge applications. And through Samsung's innovations and key algorithms, we believe that we can provide the additional benefit and advantages to our customers so that they can drive their own business opportunities, then increase in revenue and cost savings. This certainly helps the industry and our operators to deploy the next level of cutting-edge solutions.
Excellent. Well, thank you so much for all of that insight, Shamik. I think it's been really educational and informative. So everyone out there watching, I hope that you enjoyed Shamik's presentation as well. Everyone, thank you so much for tuning into this episode of Networks Tech Talks presented by Samsung. We'll, of course, be back soon with more educational sessions. But until then, I've been your host today, Tyler Kern. Thanks for watching.